3, 2, 1, let's go. Alright, so we are jumping in to a brand new topic. Alright, let's set the stage. So, we have now spent a lot of time looking at second-order linear differential equations. So, specifically, one that we're very acquainted with and know how to handle are the second-order linear constant coefficient non-homogeneous differential equations. So ones that look like this. Find me a function y, so that when I take the function y, its derivative and its second derivative, scale them by constants a, b, and c, add them up, we get our function f of t. Okay, so we know how to handle these, right? We've learned how to first solve the non-homogeneous by going to the auxiliary equation, and then find a particular solution by either using undetermined coefficients or variation of parameters, and we've even seen what to do when the coefficients are variable, and we saw that that's a can of worms. Alright, well, there is a different can of worms that we're going to open up today. Now, the methods I just described, using undetermined coefficients or variation of parameters, totally work so long as f of t is something nice. Now, we've seen some f of t's that maybe you don't think are nice, but here, when I'm saying nice, right, if f was a polynomial, if f was an exponential, if f was a sine or cosine, undetermined coefficients do the job. If f was something a little spicier, like log or secant, well, then variation parameters come and then it saves the day. Alright, now, what happens if the right-hand side is something outside of that realm? Right, what if it's something like this piecewise function right here? Right, so this function is 0 for all inputs less than 1, and then 1 for all inputs greater than or equal to 1. So it turns on when t hits 1. Now, why would we care if this was the right-hand side? Well, in terms of mathematical modeling, this would naturally occur, right? Nothing is happening, and then a switch has been turned on, right? Like, so so if we think about it in terms of a mass spring, you've come in and, right, at time equals 1, a constant amount of external force is pressed, and we're going to oppress the spring, let me tell you. Right, and as you can imagine, maybe it's not necessarily something that's digital, it could be analog. Maybe after time equals 15, it slowly starts getting some external forces introduced. So these types of things are pretty natural in the realm of mathematical modeling, so we want to now go, alright, well, how can we solve these, right? We still would solve the homogeneous as normal, but now the non-homogeneous is introducing, this is asking, well, what do we do? And as we're going to see as we go forward, the methods we know, undetermined coefficients and variation of parameters, they can't handle these sorts of things. So we're going to learn, starting today, one of the tools that can be used. Not the only one, but a pretty good one. Alright, so here is the new tool. So stare at this, digest this, get a good look at this, because for the next couple of videos here, this is our life. This is our life now. Alright, so a lot to unpack here. Okay, so what is the Laplace transform? So it's named after a mathematician, Laplace, a name that you'll probably run afoul of every so often, calling something a Laplacian type thing. It's a name. I actually don't really have any fun facts for Laplace. I feel like his life's probably unremarkable. I'm saying that, I'm gonna go look at the Wikipedia page later, and there'll be something crazy in there that I'm like, oh really, Laplace did that? But anyway, so the Laplace transform. So what does this do? It takes a function f of t, and it creates a new function, capital F of s. Okay, so note there's kind of a change of variable going on here. We're taking a function whose independent variable is t, and then we're using that to create a new function whose independent variable is s. So what you can think is we take this function f of t, and then for any s, we compute this integral. So note this integral will eliminate the t variable, Right, it will integrate it out. And now, another thing to note, of course, is that this is an improper integral, so it's technically a limit. We'll see that in action in a moment when we actually compute some Laplace transforms. Right, also note we're talking about a function we are implicitly assuming that it's defined from 0 to infinity, otherwise this interval wouldn't make any sense. So again, we take a function whose variable is t, and we create a new function whose variable is s, where we take s and then compute this integral with respect to t. So right here we see again some multivariable methods helping us out in differential equations. Shouldn't be too surprising. Okay. So, again, exactly what I just said. Note the key thing here to keep in mind, sort of conceptually, we're taking a function and we're creating a new one. So it has an input coming from t, and we're creating a new one who has an input coming from s. So we're taking our function and transforming it. Okay. So when it comes to denoting the Laplace transform, so one thing that we'll do is we'll call the Laplace transform of f, capital F of s. A fancier way of denoting it is with a very well-drawn L, and then some curly braces around your F of S. And if you look at this and you're like, that's like death by notation, yeah, it is a little bit. So when it comes to this, sometimes we'll drop the of s. In the same way when we're talking about a function, we drop the of t, like as I did right here. So if those disappear or reappear as we go on, note that I'm probably doing it intentionally, either to make it read better or to emphasize which variable is going on. Okay, so yeah, there you go. That's the definition of a Laplace transform. So talk is cheap. Let's actually compute something. Okay, so let's get a feel. So we're going to take the constant function 1 and transform it using Laplace. Okay, so there's all the stuff. Let's unpack it. Okay, so Laplace transform 1. So again, we're taking our independent variable t and replacing it with an independent variable s. And note, our function doesn't depend on t, so that's fine. So when we plug it into the formula, we'll have e to the negative st. The multiplied by 1 doesn't matter. So then we'll set the integral from 0 to infinity e to the negative st dt. Improper integral, so yes, do the limit. Don't do the freaking pretending infinity is a number. This thing right here, not a number. Not a number. Do not treat it like a number. It is a symbol, right? Just when we were talking about infinite series, that is just a thing. That's notation. That's like trying to plug in that's like saying integral sign plus dt. It doesn't make any sense. Especially with infinity, I'm like going on a little mini rant right now. Because with infinity, like infinity plus infinity, fine, that usually makes sense. But like infinity times 0 or infinity minus infinity, those undetermined forms have incredibly right. They're trying to make decisions about algebra and the infinite are oh boy. Anyway, let's get back to this integral. So this integral right here is not too bad to do. So note it's equal to that. Plug in n, plug in 0, take the difference, and now take the limit. And now here's something that's going to happen a lot with Laplace transforms. There's going to be a lot of cases where we'll take limits, and we're going to need to make decisions about what s is equal to. Right, so for example, if s was not bigger than 0, if s was less than or equal to 0, this term here actually wouldn't go to 0, this term would blow off to infinity, because of the capital N up here, right? So if s was negative, this whole thing goes positive, and then as you let n go to infinity, well, this gets gigantic, so it wouldn't actually converge to anything. So note that our function had a domain from 0 to infinity, and the transform also has a domain from 0 to infinity, but now note we're going to have to exclude 0, where before we could include it if we wanted to. Again, it's an integral. You don't really need to be defined at the endpoints in order to do the integral, but it does get dicey, so... Anyway, so the Laplace transform of the constant function 1 is a variable function 1 over s. That's interesting. Though we went from constant to variable after transforming it. Okay, so keep that in mind. And again, like I said, keep these domain things in mind. So again, here's a running theme for this course. There are these subtle domain issues that need to be addressed when you're solving differential equations. We keep like dipping our foot into the pool, but we haven't fully jumped in on that. If you were going to do some hardcore diffie Q, you're doing some real serious theoretical work with differential equations, you'd be spending so much time like messing around with the domain. I'm not even joking. You'd probably spend like 90% of your time going, all right, what's the actual domain of this damn function? Yeah, I went to a talk once, and it was about differential equations, and the guy basically was going off of it. Like he spent like weeks trying to figure out what the domain of his function needed to be, because he had like an idea of what it was, but like he didn't know like what the boundary of the like. So yeah. Anyway, he knew it went up to infinity too. That was the other thing. He was very excited he proved that. And so that's a total side note. I'm going off the rails here. When you solve diffie Q, when you're doing diffie Q, like theoretical diffie Qs, like you don't care what the actual solution looks like. You care about its behavior. Which anyway, let's actually get to some stuff. Okay, so hey, how about this function? This piecewise function, can we Laplace it? Yes, we can. So how does this Laplace? Well, it's very similar to one we just did, but there's one huge difference. So plug it into the equation. Now note, for t values less than 1, it's equal to 0. So in the integral, we don't care, right? It's 0, so no area under the curve, it's gone. Now for 1 beyond, right, so that ends up basically being the same, but now there's a t of 1 that gets plugged in rather than t of 0, so I pick up an e to the negative s, and again, the same deal, I need s strictly positive for this limit to actually go to 0. And there we go. All right, nice. So that function that's motivated us, it's the Laplace transform, pretty easily computed. And you'll see in the homework there's a bunch of piecewise function Laplace stuff that I'm going to make you do. It's a good time. But, alright. How about another one? Did you get all this? How about this? What about this? Oh god, it's too much. Alright. Anyway. Okay, alright, so let's Laplace transform an exponential function, e to the 2t. Alright, same deal. You plug it in. It's a limit like this, and there's a very good reason I wrote it like this, because it cleans up nicely when you do all the integration. So, right, note, I didn't need to pull out this negative s like this. I could have left it as 2 minus s, but as you can see with the integration, it sort of balances out and ends up being nicer. So that's the math decision I made there to write it like that. Right, yep, and the usual stuff, you plug it in, and now here, like greater than a, what is that? It needs to be a 2. Let me fix that for you right there. Alright, and whenever it feels like it, there we go. Okay, so again, here we see the Laplace transform e to the 2t, 1 over s minus 2, that's nice. Very similar to what the Laplace transform of the constant function 1 was. Remember, the constant function 1 Laplace transform is the 1 over s. Here, 1 over s minus 2. Very similar, even though 1 and e to the 2t are wildly different functions. That's interesting. Now, note, again, domain things, the only way to make this limit actually go to infinity would be as if this term right here was positive, which means I need s bigger than 2. Right. So, again, we're not going to get super sweaty about all that, but it is important to keep these sorts of things somewhere in your mind. Okay. All right. That being said, so we've now computed 3 separate Laplace transforms. Note that we're being a little, we're being bad. We're being a little bit bad, because we're going into these things assuming that the function actually has Laplace transforms. Right. It's very possible that I do a computation and I give you something, but it's meaningless if I didn't know beforehand that it actually existed. So it's very right, and don't fall for the trap of, well, I computed it, so it must exist. It's like, well, you need to be a little bit careful about that. You could have computed something that doesn't actually exist. That doesn't mean, right, just because you computed it doesn't mean it's real. All right, so let's talk existence. So your book goes into way more detail than I'm going to go into. I'm going to keep it as simple as possible. It's worth noting there's a bit more that could be said here, but I'm going to stick to the most basic thing. So a function is said to be of exponential order if you can find constants m and alpha so that the function, basically its graph, gets stuck between that scaled exponential. So that's all this is saying, is that if you look at f of t, there is an exponential that is scaled, stretched, or compressed, whatever this m in the alpha. By the way, the book used c. All right, I used alpha, so it says meat. You know, we gotta you gotta find the humor somewhere in this. But anyway, so it's basically saying that the graph stays within an exponential window, which is a very huge window, by the way. So a function that satisfies this, a function of exponential order, if you were to look at its Laplace transform, if you were to look at this integral, well, the f of t doesn't exceed that, the m gets pulled out, and then, oh, hey, look, I get that same integral that I literally just saw. I know what that integrates out to, and that's good for s greater than alpha. So not only do we know our function of exponential order, find the constants m and alpha, not only do I know that it's got a Laplace transform, it actually tells me a potential set of inputs from my Laplace transform. So, okay. So in other words, if you're of exponential order, your Laplace transform exists, and depending on the constant you get up here, that'll tell you s values that are legitimate. Right. So as long as you can bound this integral, you know that it actually has to exist. So there we go. So with that being said, from this point forward, anytime we study a function, we're talking about its Laplace transform, the assumption here is that it is of exponential order. So pretty much all of the functions you can think of are of exponential order. Every polynomial is of exponential order, sine and cosine are of exponential order, exponentials are of exponential order. For something that's not of exponential order, e to the t squared is not of exponential order, and in fact that function does not have a Laplace transform. Your book goes for the details. I'm not going to go that off the rails, but it is worth noting there are functions that don't have Laplace transforms, even pretty reasonable looking ones like e to the t squared. Although if you've ever done anything with an integral involving e to the t squared, you know it's not reasonable at all. Anyway, so that being said, here is our general sort of, when it comes to existence, we're going to assume this, and it's worth noting that this comes along with a limit that we're going to use, so that's why, this is really why I'm taking the moment to even talk about this. We're going to need this limit a little bit later on. So a function of exponential order has this very nice property that not only does the Laplace transform exist, but the function that we use to create the Laplace transform goes to zero. So you can kind of think about this when it came to series. When a series converges, that means the limit of the stuff inside of it have to go to zero. And we are explicitly going to need this limit in a little bit. So, alright. So anyway, that's just a general comment about the existence of a function's Laplace transform. There are functions that do not have Laplace transforms, e to the t squared being one of them. But for the most part, all of our favorite functions that show up as solutions of DEs are of exponential order and thus have a Laplace transform. And furthermore, satisfy this very nice limit right here. Okay, so that being said, let's start building up a lexicon. Let's get a little library of useful Laplace facts. So the integral of e to the 2t, if you really looked at it, you may have noticed something. Especially the answer. Well, that looks like I shifted the solution for the Laplace transform of the constant function 1, I shifted it by 2. Right, and in fact, we get this following equation right here, which is called the translation on the s-axis formula, or equation, whatever you want to call it. Right, so this e to the at comes in, and, right, the s value has just been shifted. So, multiplying a function by e to the at, if you try to take its Laplace transform, it simply just shifts the input. So, in particular then, e to the at, the Laplace transform of this will always be the Laplace transform of 1, s now shifted by a, and thus our example of e to the 2t giving us the Laplace transform 1 over s minus 2. Now we see why that happens. So it doesn't matter, anything could be here and you can experience the shift. Cool. Nice. Now, it's worth noting that this formula does not care that a is a real number or not. This is completely and utterly legitimate if a is complex. And because of that fact, if I look at e to the I at, I bet I could probably figure out the Laplace transform of my trig functions using this formula and Euler's formula. Ah, that's our next target. But before we get there, let's talk about probably one of the most important things about the Laplace transform. The Laplace transform is linear. Now, what does that mean? It's supposed to obviously conjure up this idea of a line maybe in your head by its name, but linear in mathematics, because we've kind of already discussed, really means that scaling and addition do what we expect them to do. So, in other words, if I scale a function and take its Laplace transform, I could have taken its Laplace transform and then scaled it and gotten the same thing. Likewise, if I want to take the Laplace transform of a sum, I could take the Laplace transforms individually and then add them up. So we've seen this before in calculus. We saw, right, the derivative of a scaled function is its scaled derivative. The derivative of the sum is its the sum of its derivatives, and we saw that with integration as well. And Laplace transforms were created using integration, so not surprising that they are also linear. And one nice thing this lets us get away with is effective computation. So if I wanted to take the Laplace transform of 4e to the negative 2t minus square root of 2e to the pi t, I don't need to plug that into the integral and work out the details. I already know what the Laplace transform of e to the at is for any a value. Since I now know that it's linear, I can break it up. In terms of summations, I can pull out all the scalars and then compute these individually and get that. So in the same way that we handle derivatives and the same way that we handle integrals, right, break it up, pull out scalars, and take the derivatives of the individual pieces we like. And the same thing is true for the Laplace transform, and there we say. All right, so that's kind of our goal too for today, is to build up this library and find all these nice little results. So when it comes to taking Laplace transforms of things, we can always break it down to these bite-sized pieces. All right. So now equipped with this, I can tell you what the Laplace transform of cosine and sine need to be. So 1 over s minus I times a, that's the Laplace transform of e to the I at. By Euler's formula, that's cosine of at plus I sine of at, and then that splits up like that. So I'll have a Laplace transform of cosine of a plus I times the Laplace transform of sine of at. So if I want to figure out what the Laplace transform of cosine is, well, this term here on the left, I just need to get this to look like something plus I times something. The thing not being multiplied by I is what the Laplace transform of cosine needs to be. The thing being multiplied by I is the thing that the Laplace transform of sine of at needs to be. So let's do just that. So the trick, if you've ever experienced complex arithmetic, is to do something called multiply by its conjugate, right? So when we do that, we know that in the bottom, we'll just pick up the first term squared plus the second term squared, so the real part and the imaginary part like that. And then we split it up, and so now we can match cosine at with this term right here. We can match Laplace transform of sine with this term right here. And ta-da! There we go. Laplace transform of sine and cosine. We now have formulas for them, and I didn't have to compute any integrals, right? I only had to do the integral for e to the at, and then from there, complex arithmetic comes and saves the day. All right? Very lazy. Don't want to do that integral. Right, if I want to directly compute the Laplace transform of e of cosine of 2t, right, you're integrating e to the negative st cosine of 2t. Do you want to do that integral? Because I don't. All right, speaking of integrals I don't want to do. Yeah, f of t, let's say, if you were to plug that in, you would need to do the integral 0 to infinity of e to the negative st times t dt. That sounds awful. Well, good thing I've got some techniques for you today. Okay, so, right, let's digest what I've got going on here. The Laplace transform of t, right, like I just said, you'd do the integral from 0 to infinity, e to the negative st t dt. Now, if you wanted to do this directly, without any savory techniques that we're about to see, what would you have to do? Well, you'd have to integrate it by parts and go through that whole little song and dance. Screw that. One of the features of the Laplace transform that we've seen so far and discussed is that it's multivariable in a way, right? There are two variables, t and s, running around. I'm integrating with respect to t. Well, if I look at this and think about it in terms of s, it looks a lot like the derivative with respect to s. In fact, it is the derivative of this function with respect to s. T does not care about s, so we can pull it out of the integral. Now, that move right there, this move right here that I'm doing, interchanging differentiation integration, I'm allowed to do that because I have a PhD in math and I know what uniform convergence is, so I can explain why this works the way it does. Although if you were to ask me to rigorously prove this, I probably couldn't, but don't tell nobody. But are you allowed to do that? You're allowed. It's fine. You can totally get away with interchanging the order of differentiation and integration. This is completely and utterly legal. I'm hand-waving a lot of technical details to pull this one off, though. I do want to stress that you would need to really justify it. I mean, it makes sense, right? This integral only cares about t. This derivative only cares about s. Who cares the order in which you do them? But, I mean, there's some pathological cases where things wouldn't work the way you want. For us, though, we got away with it, and it's fine. And then, oh, hey, look what I got here. That's the Laplace transform of 1, negative. Negative 1 over s, take its derivative with respect to s. Boom, 1 over s squared. Laplace transform of t, I've solved it. Nice. So, in fact, this was just a special case. Specifically, if you multiply any function by t and look at its Laplace transform, right, this right here, in terms of s, is always the derivative with respect to s, right? This function only cares about t. This t is showing up from the derivative with respect to s by the chain rule. Right, and there's a minus sign that disappeared, so there needs to be a minus sign here. Pull everything out. What do you have left over? Just the Laplace transform of f. So now we've got a formula for the derivative of the Laplace transform of something. It's the Laplace transform of it times t. That is a formula, man. I love this. This formula is so crazy. Like, really, look at this for a second, right? If you want to compute the derivative of something, multiply it by t. It's crazy. And hey, you can keep going. So if you were to take the Laplace transform of t squared, well, one of the t's can be peeled off, and we'll get negative the derivative. And then you can peel off that other t with another derivative and another negative, so it goes positive. So in general, the Laplace transform of t to the n of f of t is negative 1 to the n the nth derivative with respect to s. And, oh boy, yeah, look at all those parentheses and brackets. Right, if I really wanted to, right, I'd really need to include of s right here to emphasize the Laplace transform as a function of s. But we know that, so, like I was saying, notationally can get pretty, it's pretty boring, you know, a lot of, I mean, this isn't that bad. This isn't that bad, to be honest. I've seen worse. Alright, so that being said, we can now, list off the Laplace transform of all the power functions. Laplace transform of 1 we figured out. Laplace transform of t is 1 over s squared. Laplace transform of t squared then would be the negative derivative of the Laplace transform of t, which would be 2 over s cubed. All right, just take the derivative, and then keep going. And nothing's stopping us from going off to any power we want. So in fact, for any non-negative integer n, we've got the Laplace transform of t to the n is n factorial divided by s to the n plus 1. And again, where n factorial is the following: 0 factorial we take to be 1, and n factorial for n strictly bigger, greater than or equal to 1. Not just strictly bigger, though. It is n factorial of 1 is undefined. We don't know what that is. There we go. Is you multiply up all of the functions that preceded. We've already encountered this when we were dealing with series, right? Factorial of a non-negative integer is very pervasive in mathematics. It appears pretty much in every branch of math. It's an incredibly important object. So there we go. There we go. So now we have a formula for the Laplace transform of t to the n for any non-negative integer n. So now, in fact, we can compute the Laplace transform for any polynomial. So we've got a lot of functions we can take the Laplace transform of now. Any polynomial, any exponential, Sine and cosine, no problem. We can Laplace them. And now, in fact, we know a bit more. If I did e to the t times sine of t, I know how to Laplace that because multiplying by something by e to the t will simply translate the s-axis. Furthermore, t times sine of t, I could take the Laplace transform of that because there's going to be a negative derivative that shows up. So we actually have a lot of tools now to take the Laplace transform of a wide array of functions. Nice. All right. Now, that formula that we just discussed, first of all, something about that formula should be really irritating. We got this n plus 1 down here and an n up there. That sucks. That's lame. Now, if we're looking at this formula, that seems to indicate that the Laplace transform of the square root of t, which is t to the 1/2 power, it should look like this. I mean, that stands to reason. It should see an s to the 3/2 in the bottom. But factorial 1/2, that doesn't make any sense. Right, how does factorial work? You give me the number, and then you multiply by every preceding number until you terminate at 1, right? So you're removing 1 as you're doing the multiplication down. Think about that for 1/2. It's 1/2 times, take 1 away, negative 1/2, take 1 away, negative 3/2, right? That doesn't terminate. That will not stop at 0. That will just go off. So 1/2 factorial doesn't make any sense. Ooh. Get ready. Buckle up, buckaroo, because I'm about to blow your mind. Alright, so let's actually look at the Laplace transform of t to the r. Okay, so that looks like this. Where r here, we're going to make our lives mildly easy and just say r is any strictly positive real number, but you can get away with complex numbers, but let's not. Let's not go too. Let's not go crazy. Let's not go nuts. All right. Okay. So let's say you want to take this Laplace transform. Okay. I am going to make some substitutions to make life easy. Let's let s be st. Okay. Now, note that means z would run from 0 to infinity. T then is z over s, and dt now, well, I can line that up with dz over s. So if I were to make all of those substitutions, so here I'll have a e to the negative z, the t, I'll get a z over s to the rth power. dz comes in. I'll pick up a 1 over s here, right? 1 over dt is 1 over s dz. And then here we see, hey, s to the r, s to the r plus 1 showing up in the denominator. All right, so we expected that. That makes sense based on the Laplace transforms of t to the n, where n is a non-negative integer. And then that leaves us left over with this integral right here. All right, well, that integral is probably incredibly important. So let's take a closer look at this. All right, so again, the Laplace transform of n factorial has an s to the n showing up in the bottom. So we're trying to figure out the Laplace transform of t to the r for any power, when we've seen an s to the r plus 1. So here's that missing piece then, the thing that we need to replace the factorial. Okay. So this gets a name. The gamma function is defined to be capital gamma of r, where you integrate from 0 to infinity, e to the negative s, e to the negative z, and then z raised to the r minus 1 power. So note specifically that r plus 1 then lines up with that integral that is shown up for us. So the gamma function is an example of one of our favorite types of functions that we've talked about, of course, the special functions. It's probably like the quintessential special function. Most textbooks on special functions, they start off with the gamma function. The gamma function plays a humongous role in mathematics. We're about to see how it relates to the factorial. And because the factorial is so pervasive, the gamma function then ends up being very pervasive. The gamma function has got a lot of interesting properties. It's also tied up with the Riemann hypothesis, which, if you don't know, is the most famous unsolved math problem as of this recording. So it's the importance of the gamma function probably All right. So note then that the Laplace transform of t to the r is s to the r plus 1 on the bottom, and oh, look at that thing. Oh, so beautiful. Gamma of r plus 1 on the top. There we go. Now that's a formula. That looks so much better. So note then, because we know what the Laplace transform of t to the n is, that tells me that the gamma function n plus 1 is n factorial. So the gamma function can be thought then of as an extension of the factorial function. So it lines up with all of the outputs for the factorial, but it will fill in all of the gaps, right? So for any positive real number, if you were to try to plug it in, we can get some gamma information. So it's good. So it's a significant improvement, in my opinion. So, all right, nice. Okay, so now that we know that's true about the gamma function, so now let's actually explicitly look at the Laplace transform of the square root of t. So the Laplace transform of the square root of t then needs to be s to the 3/2 in the bottom, gamma of 3/2 in the top. So that means we need to compute what gamma of 3/2 is. That means you need to do the integral from 0 to infinity of e to the negative s square root of z. And I'm just going to tell you what that integral is. It's square root of pi over 2. And I'll just say that this is not an easy integral to compute. This integral is very tricky. It's an example of something called a Gaussian integral. And yeah, the easiest way to do this is to use some Calc 3 tricks. Basically, you take your integral and you convert it from Cartesian to cylindrical, and you go from there, and I'm not going to even touch that. But there's a way of integrating. There is a way of like really slickly handling this if you've got some Calc 3 tools. But I'm not going to get. I'll just say this is what you'll get. And so now we've got the Laplace transform of square root of t, square root of pi shows up because, you know, why not? So note something. Since gamma of 3/2 is 1/2 plus 1, and gamma of n plus 1 is n factorial for non-negative integers, this means that I could technically say, if I wanted to, the factorial of 1/2 is square root of pi over 2, because what other value was it going to take? And this is one of those things where, like, you look at that and you just got to go, like, well, but how did the chips land there? You know, like how did that end up being the right value? If you were like, what should factorial of 1/2 equal? Right? You would never go like, pi probably shows up. Why would you ever think pi does? It's so utterly surprising. Really, one of those results in math that's just sure, fine. Really interesting and really revealing that like pi is the ratio of a circumference to your diameter. Like how is this sort of stuff happening? You know, it's so bizarre. But anyway, that's neat. This is neat. This has all been neat and very fun. But there should be a question. There should be a question in your head by now, because we're almost about 40 minutes into this, and you should be going, all right, when are we getting to the fireworks factory? Okay, I want to solve differential equations. How do we use the Laplace transform to do this? All right, well, let's take the Laplace transform of a derivative. And then we're going to see that it does something really amazing. Okay. So let's set up that integral. That integral will look like this. And I'm sorry to report, I'm just so sorry to say, I don't have any fancy tricks for you for this one. You just got to integrate this thing by parts. So pick the thing who's a derivative so we can integrate it. Pick the other term so we can take the derivative of that. You get this, plug it all in, and yeah, it's a bleh, look at all this freaking, look at all this integral vomit. You know, you just gotta work out the details. Now, the only thing going on here that's really worth pointing out, and I've already set the stage for it, this limit right here, this goes to 0, because when we're studying Laplace transforms, our functions are of exponential order. So that, again, right, we know this limit here goes to 0, right, and that's because there's this implicit understanding that these functions we're studying satisfy that condition at the very least. All right, so that is basically it. Now, if we look at it, we see, hey, that's just the Laplace transform, right? So there's a lot of details going on here, a lot of P's and Q's, a lot of, I's to be dotted, T's to be crossed. So if you want, this is a good time to take a little pause, take a little break, and really kind of follow through all the calculations that are going on. They're not the most enlightening, but they need to happen because they now give us a formula for the Laplace transform of a derivative. Okay, so specifically, after doing all this very wonderful work, we now know that the Laplace transform of the derivative of s is s times the Laplace transform minus f of 0. So let's repeat that. Now, first of all, that shouldn't be too surprising that you take your function and you multiply it by s, because we've already seen the derivative of the Laplace transform is the Laplace transform of multiplying the inside by t. So this showing up isn't too surprising. What might be a little irritating is this minus f of 0 that shows up, and just the factor of just because integration occurred, this kind of shows up. So we've now got a formula for the Laplace transform of a derivative. And once you got a formula for a derivative, you can do it again. There's the formula for the second derivative, note an s squared, two derivatives, showing up, and f of 0 and f prime of 0. And it's worth noting that you can keep going. You can keep doing this. There's a formula for the Laplace transform of the nth derivative, but we're never going to go beyond the second one. So we'll leave it at that. And before we wrap things up today, here's a little thing to digest for a brief moment. So we talked about the Laplace transform of t to the n, where n is any non-negative integer, and then we discussed how you could figure out what the Laplace transform of t to any power would need to be. As we noted, there's a relationship between powers and derivatives. I wonder if there's some way to do like a half derivative, like a 3/4 derivative or something like that. Oh, I wonder if that's called fractional calculus, and I wonder if that's the thing. Huh. Well, let's wrap things up today by seeing how we can use the Laplace transform to help us with differential equations. Okay. So here's a first order, linear, initial value problem. Right? We know exactly how to solve this, right? This is a first order. You do your usual method for linear, get your integrating factor, yada, yada, yada. What if I were to hit this thing with a Laplace transform? Let's dissect that. Let's break that up. Okay, so on the right, we have a 9. The Laplace transform of t is s squared, 1 over s squared, so we get that. Right-hand side's fine. Laplace transform of linear, so it breaks up the way you expect, like this. Okay. And we just discussed what the Laplace transform of the derivative needs to be. Multiply the Laplace transform without the derivative by s minus y of 0. In this case, it's 1. I told you that information. So note, taking the Laplace transform removed the derivatives from the equation. And now here, I can clean things up. Hey, s plus 3. Ooh, that looks very familiar. Add the 1 over, divide the s plus 3 over, and now my differential equation has turned into, find me the function whose Laplace transform looks like this. So we have once again defeated a differential equation by turning it into a different type of problem, right? Rather than actually trying to find, a function whose derivative satisfies this, I've retooled it into a different problem. Find me a function that has this property. So we've turned this initial value problem into an inverse Laplace problem. I wonder if that's what we're going to talk about next. Well, I guess we'll have to find out next time.